Here's the data for each object. You have to find the final velocities of each one. Use conservation of energy and momentum. All right, you work on that, pause the video. Here comes the answer. Now here comes more data. Look at the kinetic energy and the potential energy. The total energy is going to stay the same. Okay, we have a little bit of error. That's computer round off error. The total momentum stays the same. That's the center of mass. Let's watch the motion of the center of mass. The velocity of the center of mass did not change. Now that the masses are no longer equal, the problem's a bit harder. So don't bother trying to solve for two unknowns. Just just check out the momentum and see if it adds up to the same before and after. And now let's watch that center of mass motion again. It's a little deceiving, but that center of mass motion does not change. Now this one's going to be a lot easier to find the final velocity because it's an inelastic collision. They're going to hit and stick. So you got the data. I'm turning it off. You try to solve for the final velocity. All right, we'll turn the data on. Look at the total energy. It's 9 joules. Watch what happens. Hey, we lost some energy, didn't we? It's no longer elastic. The internal force is friction, not an elastic spring. So the momentum, if you notice, the momentum is going to stay at 6. Look at this. It stayed at 6, but the total energy dropped from 9 down to 6. Momentum is transferred even though energy is lost. Let's see that center of mass now. Watch the center of mass. Oh, the center of mass is moving with the object now that they're stuck together. There's no other choice. Now, what do you think is going to be the outcome of this collision? It's inelastic. They're going to hit and stick. There's the data. You find the final velocity. Here it goes. Ah, very good. Let's take a look at the center of mass. Turn on all the data. Whoa, the total energy went to 0. Yeah, there's nothing there. There's no more. It's not going to shoot back out. It's not like it stored the potential energy. Here's another inelastic collision. Look at that data. They're going to hit, they're going to stick. So there's only going to be one object. You predict the outcome. Wow, the little guy knocked the big guy right back. How come? Well, the sum of the momentum is negative 2.25, and that means the answer has to be going to the left if they hit and stick. Let's look at that center of mass motion. Yeah. All right, check out the data on this one. The initial velocity is 0. There's a spring between them. It's called recoil, or as we saw with the carts, an explosion. Okay, we have two unknowns. This is going to be hard to find. Let's just test it and see if the sum of the momentum stays the same. The momentum's 0. Here we go. And it stayed 0. And the total energy is 60.5 joules. The kinetic energy is now 60.5 joules. Where did it come from? The potential energy is 60.5 joules. That makes sense. Hey, the center of mass, let's see what it does. Stays right there. Okay, recoil 2. Oh, let's just run this and see what happens. Oh, that was just, okay, that was just for you to see if you could do it. All right, here's an inelastic collision. Oh, looks like a little bullet is going to shoot into this big guy. I'll get rid of the center of mass. Turn off the data now. What the heck? It shot right through him. Do you think momentum was still conserved? Yeah, this happens all the time with ballistics. Cops are checking out the crime scene. Bullet passes through something. It moved. Momentum stayed constant. Now, is it possible that we could have an object attached to another one? Let's see what happens here. Well, this is what happens in chemical bonding. An object, a molecule, an atom hits another atom and they start to bond and they form this vibratory oscillation there. Let's try looking at the center of mass. Now take a look at the kinetic and potential energies. They keep changing. The total energy is staying fairly constant. It should be exactly constant. That's an error due to the computer round off. I'm running the thing kind of fast. I should really run it slower and you'll get way less error. But the momentum stays constant. Well, let's see what this does. That would be like two hydrogen atoms in a bond. Alrighty, I think we're done. Wait till you see what's coming up next. Notice how they're not exactly lined up now. These are going to be like two charged particles, one at rest, the green one is moving. Watch what happens. They repelled each other. Can you figure out the velocity of these objects? Maybe you ought to just see if that momentum stays constant. Hey, it's still at 4.5. And it's got to be to the right. Let's trace the motion of these objects. Oh, it's so two-dimensional, isn't it? The total energy stayed the same. Let's take a look at the center of mass. Even in two dimensions, the center of mass motion does not change because there's no external forces. Notice also the total energy stays the same.